Welcome to The Explainer. So let's talk about the paradox at the very heart of AI. You see something like ChatGPT write an incredible poem or a super complex piece of code, and you just think, wow. But what if I told you it doesn't understand a single word of what it just wrote? How on earth is that even possible?
Right? I mean, this is the question. It's got everyone from the top engineers in Silicon Valley to philosophers scratching their heads. The stuff these models produce feels so intelligent. But is there actually a mind behind the curtain? Well, that's exactly what we're going to dive into today.
Okay, so to really get our heads around this, here's how we're going to break it down. We'll start with that core paradox. Then we'll lift the hood on the magic inside. After that, we'll look at how it's actually trained. Tackle the big question, is it a mind or just a mimic? And finally, we'll talk about what it means to have this new kind of alien intelligence.
All right, let's jump right in. The prediction paradox. You've probably heard the phrase autocomplete on steroids to describe these models, right? And, it's a fantastic starting point. But trust me, the steroids in that analogy, they're doing some seriously heavy lifting.
So at its absolute core, what is an LLM doing? It's kind of mind-blowing how simple it is. It's a prediction engine. That's it. Its entire job, the only thing it's ever trying to do is guess the most probable next word in a sequence. Every poem, every line of code, every answer. It all comes from that one single task.
Okay, let's make this super clear. If you type in Mary had a little, the model doesn't know the nursery rhyme. It has no idea who Mary is. What it has done is scan a massive chunk of the internet, and based on that data, it's calculated that the word lamb has, say, a 99.9% probability of being the next word. And a word like, cower, that gets a probability score of pretty much 0. It's all just a numbers game.
So, the big question is, how does this one simple trick, just guessing the next word, create something that can write a sonnet or debug code? How does that scale up? Well, to see that, we've got to pop the hood and look at how the magic really works. And it all starts by turning words into math.
First things first, a computer doesn't speak English. Its native language is numbers. So the first step is always translation. We take our text and chop it up into pieces called tokens. Think of them like Lego bricks of language. They can be whole words, parts of words, or even just punctuation. Then each one of those little tokens gets turned into a string of numbers, a special numerical code.
And this numerical code, called an embedding, is the really clever part. It's not just a random number. Imagine a gigantic, sprawling map of language, but in hundreds of dimensions. Each token gets its own unique coordinate on this map, and the cool thing is, words with similar meanings end up as neighbors. So king and queen are clustered together, cat and dog are close by. The AI doesn't understand what a king is, but it knows from the data that king lives in the same mathematical neighborhood as queen and prince.
Okay, so this is where the real game changer happened. This is the steroids we were talking about. For a long time, AI models, these things called RNNs, read text the way we do, one word after another. The problem? They had terrible memories. By the time they got to the end of a long paragraph, they'd basically forgotten what the beginning was about. But then, in 2017, the transformer architecture came along, and instead of reading sequentially, it looks at all the words at once, in parallel.
And this ability to see everything at once gave it a superpower called self-attention. It allows the model to look at a whole sentence and figure out which words are most important to which other words. So in a sentence like, the cat sat on the mat because it was tired, self-attention is what lets the AI connect it all the way back to cat and not mat. That kind of contextual understanding was a massive, massive leap forward.
Okay, so we've got this powerful architecture, but how does it actually learn all these connections? Well, it doesn't just happen overnight. It goes through a pretty intense 3-step education process to go from just raw data to a refined assistant.
So, step 1 is pre-training. This is where the model is just unleashed on a giant chunk of the internet. Books, articles, websites, you name it. Its only goal is to learn the statistical patterns of human language. Next up is instruction tuning. This is where it learns to be useful, where humans teach it to follow commands, like, hey, summarize this article for me. And finally, there's RLHF, which stands for Reinforcement Learning from Human Feedback. This is where real people rate its answers, teaching it to be more helpful, harmless, and align with what we actually want.
And you can see how it evolves here. It starts as this raw prediction engine, then becomes a useful assistant, and finally, a much safer model. And you know, those last two stages are absolutely crucial. Without them, all you'd have is what researchers call a stochastic parrot, something that just mindlessly parrots back the patterns it saw online without any real direction or usefulness.
Okay, so we have this thing that can learn and respond in these incredibly complex ways. And that brings us to the big, thorny, philosophical debate. Is there a mind in there? Or are we just looking at the most sophisticated mimic in history?
And you can't talk about this without bringing up the famous Chinese room argument. It's a thought experiment. Imagine this. You're locked in a room. You don't speak a lick of Chinese, but people are slipping notes with Chinese characters under the door. Now you have a massive, detailed rulebook that tells you, if you see this set of squiggles, write down that set of squiggles and slide it back out.
Now, to the people outside, it looks like they're having a perfectly fluent conversation in Chinese with whoever's in the room. But you, inside the room, you have zero understanding of what's being said. You're just following rules. You're just a symbol manipulator. And the argument is that's exactly what an AI is doing. It's mastered the rules of language, the syntax, but it has absolutely no understanding of the meaning, the semantics behind the words.
Of course, it's not that simple. There are some really interesting counterarguments. One is called the systems reply, which basically says, you're looking in the wrong place. Sure, the person in the room doesn't understand, but the entire system, the person, the room, the rule book, that whole thing understands Chinese. Then there's the robot reply, which argues that you can't have true understanding without a body, without the ability to actually interact with the physical world.
So the philosophical debate is fascinating, and it could go on forever. But let's bring it back to the real world, because the way these things are built, this purely statistical approach, leads to some very practical and sometimes very weird limitations.
Yeah, this is where you really see that this is not a human-like intelligence. For one, they hallucinate, which is a nice way of saying they just make stuff up with total confidence. They have zero real-world common sense, they don't know that you can't push a rope. And their reasoning can be surprisingly brittle. You can change one tiny word in a prompt, and their whole logical chain just shatters.
And then there are hard technical limits, like this one, 4096 tokens. This was the context window for an early model like GPT-3. Think of it like short-term memory. It's the maximum amount of information the model can look at any one time. That's about 3,000 words. So if your conversation goes on longer than that, it literally starts forgetting what you talked about at the beginning. There's no long-term memory.
And this is so important to get. These limitations, the hallucinations, the lack of common sense, they aren't bugs that engineers are just going to patch in the next update. No, they are fundamental characteristics of what this thing is. They're the natural result of an intelligence built on probability, not on consciousness or real-world experience.
So, what does this all mean for the future? Well, it suggests the goal probably isn't to try and build a conscious mind for these things. Instead, it's about figuring out how to use this incredibly powerful, but also flawed, tool. The real challenge is building human-in-the-loop systems that can leverage its amazing predictive power while having a human to keep it grounded in reality.
And that leaves us with a pretty wild final thought. For decades, the goal was to create an artificial human intelligence, and in that, we haven't succeeded. But in the attempt, we might have stumbled onto something totally different, something genuinely new, a powerful and truly alien kind of intelligence. And maybe the biggest question we're facing now is, what does it mean to live and think alongside that?